In this video, we are going to review a precipitation reaction, and we're going to look at this state where we write AQ after a formula. Recall that AQ means we have an aqueous solution, or aqueous, and that root word there means water. So when water is the solvent, if we see a formula written with AQ after it, remember that means that the ions have separated in water. So an ionic compound, remember, has a metal that has a charge and a nonmetal that has a charge. So if we have a solution of salt water or saline, a saline solution, then we would have water as our solvent. And if we threw solid sodium chloride in water, when the salt dissolved, we would not see the ions, but we would have Na+, the sodium ion floating around, as well as the chloride ion floating around. So whenever we have ions, because of their charges, then the ionic solution would cause that solution to conduct electricity. So the word electrolyte, which is quite a buzzword now, it's used to sell sport drinks, and even beer now is advertised with electrolytes in it. But the electrolytes allow for the transfer of charge. So technically speaking, pure water should not conduct electricity if there are no ions in it. Or, for example, if we have sugar in water. So I didn't make that big enough. C6H12O6. If we had sugar in water, this is not an ionic compound. So whenever we have two or more metals in solution, then we have the covalent type compound where the electrons are not transferred. So in other words, we don't have a chloride that's going to steal electrons from a sodium, but we have a bonding situation where all of those electrons are shared. And so a molecule or a covalent compound will not break apart into ions. So this type of solution would not be an electrolyte. So electrolytes will be produced, those types of solutions, as long as we have a soluble ionic compound. Another precipitation reaction that our textbook shows us is lead nitrate. And from the previous video, when we looked at the solubility chart, I said it was a great idea to remember that nitrates are always soluble. So lead nitrate, or lead 2 nitrate, is going to break apart and have 2 nitrates for every lead ion. Potassium iodide is also soluble because iodides are soluble compounds, and the exception, silver, mercury, or lead, is not here with potassium. So these both dissolve in water. If we mix these two together, you'll see in your book that this forms a bright yellow solid. And the way we would know that the solid was the lead 2 iodide, for one thing, nitrates are always soluble. So are column 1 metals. And if we look at the solubility guidelines, again we'll see iodide is soluble unless the metal happens to be lead in the oxidation state of lead plus 2, which is the case for our lead 2 iodide. So we want to get a little bit of practice using the solubility chart to determine whether each one of these 3 compounds would dissolve in water or would not. So if we remember that column 1 metals are always soluble, that's just about as important as nitrates are always soluble. So if I look at phosphate, so this is a polyatomic ion phosphate. Phosphates are insoluble, so if phosphate is with a metal, it's going to make a solid. But if we look over here, the alkali metals are the exception. So column 1 metals are always exceptions, which means column 1 metals are always soluble. So this we would write AQ after that formula. That means when that dissolves, we have 3 lithium ions for every 1 phosphate ion in solution. Okay. If we look at this formula, this would be lead 2 sulfate. So if we find sulfate, sulfate compounds are soluble unless the metal is strontium, barium, mercury, or lead. So again, the exception to the rule, lead was part of our formula. So although sulfates are soluble, lead is the exception. So this would have the state solid written after that. The last formula is magnesium hydroxide. And if you recall acid-base chemistry, we might say, well, that's a base because it's got hydroxide in it. So hydroxide is the polyatomic ion with the -1 charge. So if we look on the solubility guidelines, hydroxides are insoluble. So the exceptions to that are column 1 metals and the heavier column 2. So calcium, strontium, barium, and any column 1 metal. So we're going to see later on that if hydroxide is combined with one of these metals, that is going to be the case for a strong base. And a strong base is 100% soluble in solution. So if we look at magnesium hydroxide, hydroxides are insoluble unless they're with a column 1 metal or the heavy column 2s. So this formula would remain a solid. If we look at rolaids or Tums, an antacid, we'll see magnesium hydroxide is one of those, or this is in milk of magnesia also. So if you drink milk of magnesia because you've got a stomach ache, it's white and chalky, and that's because the magnesium hydroxide won't dissolve. So you'll have to try to drink that. Okay. So if we look at one more exchange reaction, sometimes this is called double replacement, then we could write the, well, if we actually did this, this is Epsom salt, magnesium sulfate. So if I mixed Epsom salt with lithium hydroxide, again, this would be considered a strong base. Hydroxides are insoluble unless they're with a column 1 metal, and sulfates are always soluble unless they're with one of these. So both of these would be clear solutions. If we mix these together, this metal will switch places with the lithium, and the lithium will combine with the sulfate. So when we write the formulas, we have to keep in mind the charges on the ions. So since lithium is in the +1 column, 2 lithium ions are required for every 1 sulfate ion. So if we haven't memorized the polyatomic ions, those are listed on the solubility guidelines. So sulfate, we can see here, has a -2 charge. So our formula for lithium sulfate would be 2 lithiums for every 1 sulfate. This would be AQ, because column 1 metals are always soluble, and sulfate is with it. So that would be remain dissolved in water. And then the magnesium would react with the hydroxide. Again, our charges have to be taken into consideration. So magnesium is a +2. It's in column 2 on the periodic table. Hydroxide is a -1. So in order for the charges to cancel to 0, we need 2 hydroxides for every 1 magnesium ion. So if we mix these together, we would also see the formation of a white powder. So we could say that we would precipitate magnesium hydroxide out of solution. And I'm not going to go with the complete ionic equation on this. I think I'm just going to write the net ionic equation. So magnesium and sulfate, if we look at this equation, that's aqueous, aqueous. Our sulfates are going to be spectator ions. And this isn't balanced. We need 2 lithium hydroxides here. Because this is soluble, we'd have 2 lithium ions and 2 hydroxide ions in solution. And because this is soluble, we'd also have 2 lithium ions, so our lithiums would go away. And we'd be left with magnesium. So our net ionic equation is magnesium ion plus 2 hydroxide ions would give us the solid magnesium hydroxide. And the reason we say net ionic equation is if we're doing this experiment, this is what we see happening in the beaker. So the net ionic equation is what is actually happening, or what is taking place in the beaker. Oops. Spectator ions stay in solution, so they don't combine with other metals or nonmetals. So in this chapter, another type of reaction that we still consider aqueous or aqueous is an acid-base reaction. This also may be referred to as neutralization. And so I've given us a very common acid. So if we see an H written first in the formula, then that's how we know that it's an acid. So 99% of the time that H will be written first. So this is hydrochloric acid, the acid that's in our stomach. Since this says aqueous, that means that the HCl breaks apart into 2 ions. And this is the strange case where we really have a covalent compound. So hydrogen chloride would look like that. Since hydrogen is not a metal, we have 2 nonmetals that are bonded together covalently. But when we bubble this through water, the bond breaks so that hydrogen's electron goes with the chloride. So hydrogen's in column 1, it's happy to get rid of an electron, and chlorine is in column 7, it's happy to gain an electron to become chloride. So this is a strong acid because it completely dissociates, so we'll talk more about that later. So if we mix that with sodium hydroxide, hydroxides are insoluble unless they're with a column 1 metal. So if hydroxide's with a column 1 metal or calcium, strontium, or barium, then we have a strong base which is completely soluble. So we would have the sodium ion dissolved and the hydroxide ion dissolved. And technically I should write AQ as the state under each one of these. This is also a type of double replacement reaction or exchange reaction, so just depending on what textbook you're using. So this H gets together with the OH and the Na gets together with the Cl. So we end up with HOH, which typically we just write as water. And that is not aqueous, that's the liquid. So water is a liquid. and then the sodium ion gets together with the chloride ion, but both of those ions are soluble, so we don't see salt forming in this solution, but we still have those spectator ions there. So if we mix an acid with a base, we're going to make water and a salt. So water has a neutral pH, and we'll discuss that in much more detail next semester. But a neutral pH is pH of 7, and then an acid with the hydroxide will also form a salt. So it may not be sodium chloride, but we'll still have the formation of a salt. So I've almost written the complete ionic equation up here. So if I just put Na plus Cl minus, then that's the complete ionic equation. If we cross out the species that show up on both sides of the equation, we'll see that the net reaction for any acid-base reaction is we have an H plus getting together with OH minus to make water. Okay. So I've given us one more example. This is calcium hydroxide. So calcium metal is one of the exceptions to the rule. So hydroxides are insoluble unless it's with calcium. Calcium is a +2, hydroxide is a -1. So the formula for calcium hydroxide would be a 2-to-1 ratio. And this is nitric acid. So that's also another strong acid. So if I balance this equation, balancing an acid-base reaction is easy. All we have to do is make sure our OHs equal the H's. So if I put a 2 in the front of nitric acid, then I've got 2 H plus ions to react with 2 OH minus ions. So I'm going to go ahead and write this complete ionic equation here. When nitric acid dissociates, we'll have 2 hydrogen ions plus 2 nitrate polyatomic ions. And then when calcium hydroxide dissociates, we'll have 1 calcium ion and 2 hydroxide ions. Remember that 2 means we have 2 hydroxides. And then 2 H's and 2 OH's will automatically give us 2 H2O molecules, 2 waters. And then our calcium getting together with nitrate, a +2 metal and a -1 nonmetal, would give us the formula. Well, I'm not going to actually write that. I'm still writing out our complete ionic equation. So we'd still have 2 calcium ions and we'd have a calcium +2 and 2 nitrate ions. So nitrate is a fabulous spectator ion. That means it doesn't do anything. So we cross out the 2 nitrates that show up on both sides of the equation, and the calcium stays dissolved. And again, I'm being lazy. I should write AQ under every one of these species. Water is a pure liquid, so we don't write AQ after water. So the net ionic equation for any acid-base reaction, assuming the base is a hydroxide. So we do have bases that don't have hydroxide in the formula, but for now we'll stick with the bases that do have hydroxide in the formula. The net ionic equation for any acid-base reaction is we see H plus combining with OH minus to form H2O. So we really did not need 2 and 2 and 2. We could have just written 1, 1, and 1. When we start studying the pH, we'll see that something acidic is going to have a pH value of less than 7. When we have a basic solution, which means excess hydroxide, sometimes this is written as alkaline, then we'll see that the pH value for that is greater than 7. And then if we take the pH of water, water is right in the middle of the pH scale, so the pH of water is 7. So if we have something with a pH of 7, then we say it's neutral. So we are going to study acid-base chemistry in 2 chapters next semester. But for now, we just want to be able to recognize an acid-base reaction. So an acid always has an H written in the formula and at the beginning, and a hydroxide base is going to have an OH minus in the formula. And then an acid-base reaction, the net reaction that occurs is the acid combines with the base and makes water. So that's a good way to neutralize a spill. If we spilled acid on the counter, we could neutralize that acid with a base.